And today I'm going to be discussing ramp up and multi-armed bandits. And the thing that ties these two things together is the fact that there are common ways of changing assignment weights during an experiment. And today I'm going to be discussing the problem, the changing assignment weights problem and a solution. So although I'm going to be presenting on a specific problem, I think there's some general takeaways that you can get from this talk as well. So the general takeaway is that when running an A/B test, you need to think deeply and critically about whether or not the assumptions of the method you're using matches your data. It's very tempting to use a tool you've used in the past or some commonly accepted tool that works for a lot of situations, but that may not always work for your current situation. In other words, big data and the law of large numbers doesn't solve everything for you. And more specifically, we're going to be talking about sort of implications for experiments that use ramp up on multi-armed bandits. So just some context on how a common way that web experiments are done. So let's say that a website user, they're assigned to a treatment upon first visit. And then users maintain assignment to that treatment throughout the experiment. And assignment weights refers to the proportion of users assigned to each treatment. And then the picture on the right is sort of a common ramp-up situation where early website users have a 90% chance of being assigned to the control and a much smaller, let's say, 10% chance of being assigned to the variant. And this is done essentially as a risk mitigation strategy. The variant has never been seen before by real users, so you want to put some sort of cap on the number of users that could experience this variant in case it goes terribly wrong. But usually it's the case where the variant isn't terribly wrong, and as you learn this, you progress and do get closer and closer to 50-50% assignment, 50% to control, 50% to the variant. So to illustrate the sort of a problem with ramp up, I'm going to use this simulation where I simulate data for an A/B test on conversion rates. So I'm going to simulate 2 million users who come to a website during an experiment. And these 2 million users, so 2 million is chosen to be large enough so that we have negligible sampling variation. So in other words, every time I run this simulation, I get essentially the same answers. So for that reason, you're not going to see any confidence intervals or credible intervals or plus or minus error or anything like that. Again, that's just because it would essentially be 0. So we have these 2 million users. Their first visit, and hence assignment, is simulated by this uniform distribution, where I'm just saying that the users are being assigned uniformly throughout the duration of the experiment. Then I also say users are either frequent users or infrequent users. So imagine a frequent user is somebody who visits the website, let's say, every day, and an infrequent user is somebody who visits less often, let's say once a week or something like that. And the sooner a user's first visit occurs, the more likely the user is to be frequent. And this makes sense. If somebody comes daily, they're more likely to be assigned sooner. And I simulate this with this Bernoulli distribution where I say AI equals 1 if user I is frequent, and the probability of being frequent goes up as your first visit ZI goes down. And then I say whether or not a user converts is simulated by the probabilities in this table. So frequent users prefer the variant, and infrequent users prefer the control. Now let's say you want to do ramp up and you want to change assignment weights. So we can simulate that with this sort of illustration here, where in the first half of the experiment, 90% of users are assigned to control, 10% are assigned to variant, and then in the second half of the experiment, you have 50-50 allocation. And that's just simulated with this Bernoulli distribution on the left. So if you change assignment weights, you would get the following conversion rates, and the variant would be the winner. Now let's say you hadn't changed assignment weights. In other words, you kept this 90-10 allocation throughout the duration of the experiment. In that situation, the control would be the winner, and we'd have these following conversion rates. Okay, so what happened here? Why did we get a different answer when we changed assignment weights than when we didn't change assignment weights? So the reason is because Changing assignment weights introduces a bias because it introduces a dependence between assignment time and assignment. In other words, which treatment you're assigned has some relationship to when you arrive, or excuse me, when your first arrival is. So in other words, the distribution of time-based confounders, such as frequent or infrequent user, or perhaps day of the week, the distribution of time-based confounders in each treatment is different from each other. So this is illustrated with the table on the right. The first two rows correspond to the changing assignment weight scenario, where we see that among users assigned to the control, 57% are frequent, whereas users assigned to the variant, only 33% of users are frequent. And this sort of makes sense, right? So if you remember, 90% of users are assigned to control in the first half of the experiment. So the majority of users assigned to control are being assigned in that first half. And that's when more frequent users arrive. So we have more frequent users in the control than we have in the variant. And since there's a difference in how frequent and infrequent users, there's a difference in their preference, this is causing a bias. And in the bottom two rows, we see what the distribution of frequent users would be if we hadn't changed assignment weights. So we're seeing in the control, 50% of users are frequent, and the variant, 50% of users are frequent. So that confounding variable is the same in both treatments when you do not change assignment weights. Okay, so the solution involves measuring this thing that I call epoch and modeling its effect. So I just define epoch as a period of time where weights are constant. So in the simulation, epoch 1 would be that 90-10 assignment scenario, and then epoch 2 would be the 50-50. And the reason the solution is going to work is because within an epoch, assignment time and assignment are independent. In other words, every user assigned in a given epoch is equally likely to be assigned to control as any other user assigned during that epoch. And then we're going to use a weighted average of conversion rates in the epochs. Okay, so this is illustrated with in this table here. So the epoch 1 and the epoch 2 columns, those are just the sample proportions, or in other words, the sample conversion rates of users assigned during the respective epoch. And then in the weighted average column of the table, we see a weighted average of those two epochs, where the weights are, in this case, 0.5 and 0.5. And those 0.5 weights, those are just the proportion of all users, regardless of which treatment they're assigned, who arrive in each epoch. The weights here are 0.5 and 0.5 because if you remember, users are arriving uniformly. And then the epoch point is at the halfway point. So half of all users are assigned in epoch 1 and half of all users are assigned in epoch 2. If instead the epoch transition point was at the quarter-way point of the experiment and users still arrive uniformly, then the weights would be 0.25 and 0.75. And here we're seeing that the solution, the answers you get with the weighted average solution are the same as the sample proportions you get when you don't change assignment weights. The only difference between these numbers that's just due to rounding error. That's the only reason you're seeing a difference there. Okay, multi-armed bandits are the other common way assignment weights are changed in an experiment. And multi-armed bandits are a class of algorithms that maximize reward, so conversion rates, sales, whatever, by assigning more users to better performing treatments sooner in order to take advantage of them sooner. MABs are sometimes run perpetually and not necessarily to find a winning treatment. So in these scenarios, the MAB is just always determining which treatment users get assigned to, and it's continuously running. It never stops. I think more often, this is a suspicion, but I think more often an MAB is run to maximize reward during an experiment, and eventually one of the treatments in consideration is permanently deployed. And in this situation, MAB is used basically like an experiment. Thompson sampling is a common MAB algorithm, which assigns a user to a treatment according to the probability that the treatment is best given the data seen thus far. So we're going to use Thompson sampling with the simulation that we just discussed earlier. Except this time I'm going to repeat the simulation 300 times, And that's just because Thompson sampling is a little bit noisier than just the A/B test, so there's a little bit more variation in what can happen. So I run it 300 times. Thompson sampling requires a Bayesian model. So we're going to fit the data with the following simple model, where if I indexes a user and J indexes a treatment, all we're saying here is that whether or not user I converts is dependent on which treatment they're assigned to. In other words, we're just saying that treatments have different conversion rates. And then we're just putting a non-informative beta prior on theta. Now, some of you may be thinking that this model is perhaps too simple for the real world. And I would tend to agree with you on that. But I would like to point out that the simple model differs from the data generating process. That's just the simulation, right? The only way this model differs from the simulation is by the omission of a single variable, that frequent versus infrequent user variable. In other words, we know that whether or not you convert depends on whether or not you're a frequent or infrequent user. So that's the only way the model is different than the true data generating process. And omitting confounding variables isn't usually a concern in a traditional A/B test, because the law of large numbers and random assignment takes care of confounding variables for you, right? You would expect any confounding variables to be equally distributed across the treatments because of random assignment and the law of large numbers. Now, when I do this MAB 300 times, here's a histogram of the reward, comparing an MAB to a traditional A/B test, which is 50-50% assignment. And here we're seeing that the reward in the traditional A/B test is better than the MAB 90% of the time. And here reward is just the number of conversions accrued during the experiment. And this is quite remarkable, considering the whole point of an MAB is to maximize reward during the experiment. Yet, because we're omitting just that one variable, the frequent versus infrequent user variable, it is very counterproductive relative to a traditional A/B test. Right? In fact, 90% of the time you get worse reward. And then if you were to also use the MAB to eventually deploy a treatment, you would also be wrong 90% of the time, at least relative to a traditional A/B test. Okay, so what's the solution here? You have to condition on continuous assignment time, similar to how we conditioned on epoch with ramp up. You have to model the effect of the continuous assignment time and use a weighted average over assignment time. And if this sounds difficult, that's because it is. You have to now integrate to get the average since it's continuous, and it's difficult to model the effect of a continuous assignment time on reward, at least relative to a categorical variable like epoch with just a few categories. And this solves the bias problem, but doesn't maximize reward, right? And that's the whole point of an MAB, to maximize reward during the experiment. So that makes the solution kind of ultimately unsatisfying. There is this class of multi-armed bandit algorithms called restless multi-armed bandits, which don't assume reward is constant over time. Now, I would point out that they do add, restless multi-armed bandits add assumptions about how reward is changing over time. And considering how counterproductive things were in Thompson sampling, when just minor assumptions were violated, this doesn't get you off the hook. You still have to critically assess and understand whether or not the restless multi-armed bandit, the assumptions are matching what is happening in your data. So you're not off the hook with these restless multi-armed bandits. Okay, conclusions. Naively changing assignment weights can lead to biased results. Solutions for ramp-up involve a weighted average across epochs. Solutions for MABs are a bit trickier and ultimately sort of unsatisfying. We do have these restless multi-armed bandits, but like we discussed, you have to still, you're not off the hook. You still have to understand whether or not they're working for your situation. And then MAB algorithms can be counterproductive towards maximizing reward if implemented naively. And if the goal is to eventually deploy an ARM, perhaps one shouldn't be taking on the complexities required for using an MAB. Perhaps a more robust traditional A/B test is what's right for you, especially considering if you don't have the resources or the time to make sure you get these MAB algorithms just right. And then if you take nothing else away from my talk, I hope what you take away is that when running an A/B test, you need to think deeply and critically about whether or not the assumptions of the method you use matches your data. And if you're interested in more detail, I wrote a blog post on this on the Google Data Science blog. So if you just Google Data Science blog, you should find it. Okay. Thank you.